Okay, so I think we can start. So, myself, Harish, I am a PhD student at ISER Mohali, and uh, we are here to discuss assignment 1 and 2 uh, of Algebra second course. So, yes, I hope my screen is visible and the sound is clear too. So, yeah, let's start. So, it's going to be uh, week 3. Uh, we are going to discuss assignment 1. We have already revised uh, lecture notes of week 1 and week 2. So we will try to see how much problem we can do the next 2 hours, and if we are left with some, then we will complete it in the upcoming Tuesday. So what's the date today? I think it's 16. Yes. Okay. So here comes the first question. So it says, what is the degree of q root 5 eta over q? So we have already seen fields uh, and field extensions. And so q root 5 eta is a field extension of q. And we are interested in finding the uh, degree of this field extension. As So by degree, we mean the vector space dimension of this field as a vector space over q. So yes, any guesses or answer? Nothing. So one thing is clear, that the degree should be greater than 1, right? Because this root 5 eta is not inside q. Okay. So what I mean to say is, since root 5, just so since root 5 eta is not inside q, so the degree must be greater than equal to 2. The degree of q root 5 eta over uh, q must be greater than equal to 2. And also, let say t is equal to root 5 eta, 5 eta. This implies, if we square both sides, this is t square minus 5 minus 5, and which implies t square plus 5 is equal to 0. And this implies that since root 5 eta satisfies root 5 eta satisfies mm, x square plus 5 over q, the degree of the extension must be less than equal to 2, because it satisfies a polynomial of degree 2. And combining both these facts, we get that the degree is precisely two. Okay, so I hope it's clear. If not, you can just stop me here. Otherwise, I will write the another question.
It's okay, sir.
Okay, so it's a kind of warm-up question, easy one, I guess. The second question is, uh, if you ask me, is the most crucial question of the entire assignment, and it needed uh, some theory that we already saw in during the revision of the lecture notes. So it says, what is the degree of the irreducible polynomial 2 raised to 1 by 3 plus 3 raised to 1 by 2 over q. So the options are 2, 3, 5, and 6. So if you just want to make a guess, or if this question comes as an objective question, if you just want to select a question, select an option, then there is this the solution is not difficult. You can easily choose the right options in among these four. So how you can do that? So we are interested in finding the irreducible polynomial, degree of the irreducible polynomial of 2 1 by 3 plus 3 1 by 2 over q. So you know that the degree of the irreducible polynomial of 2 1 by 3 plus 3 1 by 2 over q is same as the degree of the extension of q adjoining this 2 1 by 3 plus 3 1 by 2 slash uh, this is q, right? And you can check that uh, q 2 1 by 3 plus 3 1 by 2 as a field, uh, it is same as q 2 1 by 3 comma 3 1 by 2. That you can check. We will do a similar question later on, and now we need to find its degree, right? So how to do that? So this also this is a field extension of q 2 1 by 3, which is a field extension of q, and this is a field extension of q, also a field extension of 3 1 by 2, and that is also a field extension of 2. So here to here we have degree, uh, here we have degree for this field extension, we have degree equal to 3 because it satisfies the uh, irreducible polynomial x cube uh, minus 2 equal to 0 is the irreducible polynomial, is an irreducible polynomial. Why it is irreducible? You can just use the Session criteria and see. And other way to look at is, this is a polynomial of degree 3, and so it must have a root uh, so if it is reducible, then it must have a root, because you can break it as polynomial of degree 1 and polynomial of degree 2, and then you can see that it won't have a root. That's the other way, or the easiest way is you already know the isosceles criteria and you can use it. So it's an irreducible polynomial over q, and of course, uh, 2 1 by 3 satisfies it. So the degree is here is 3, and here the degree is uh, 2, because it is satisfies by the polynomial x square minus 3 equal to 0. This polynomial is irreducible and satisfied by uh, root 3. Okay, so now what does these things tell you? So they are field extensions. So it so they are forming a tower. So this means that the the degree of q 2 1 by 3 3 1 by 2 is equal to over q is same as the degree of q 2 1 by 3 over q uh, just give me a second. So this degree of this over q 2 1 by 3, and then multiplied by the degree of 2 1 by 3 over q. So we have a tower. So this tower we are using, and using that we get this equality, and using the another tower we will get this equality, that this is equal to the degree of 2 1 by 3 3 1 by 2 over q root 3, and that is equal to q root 3 q multiplied by this. So they both are there, and this is this is equal to 3 2, and this is equal to 3. So this implies that the degree of 2 1 by 3 3 1 by 2 q uh, is divisible by 2 and 3, and that implies that 6 divides the degree of this, right? So the options were 2 3 and 5 and 6, right? 2 3 5 and 6. So options 2 3 and 5 are not correct, and this implies the degree of this is equal to 6. So what if it's a not an optional question? So one way to answer it is in this way: if you just discard the options and this, but you might get an option like the degree. What if the one option is 12 or 18? Then you have to see that whether the degree is precisely 6 or not. So for that, uh, alternatively, alternatively, what you can do, so let t is 2 1 by 3 plus 3 1 by 2. Okay. Now what you do, you try to find a polynomial which is satisfied by this. So this implies that t uh, minus 3 1 by 2 is equal to 2 1 by 3, and that means if we take the cube of it, it becomes, right, and you expand this cube. So let's write it here. This will be t cube uh, minus 3 3 by 2 plus 3 3 t minus 3 1 by 2 t square equal to 2. Which identity I am using here? I am using a minus b cube is equal to a cube minus b cube minus 3 ab square plus 3a square b. I hope that is correct, or some mistake I have done. I think it's a square b probably here. 3, yes, here we have minus 3 a square b, and here we have 3 plus 3 ab square. Okay, so this identity I'm using, and from here what we get, we get that t cube plus 90 minus 2 is equal to 3 root 3. This is also 3 root 3. 3 root 3 1 plus t square. So we square both sides, squaring both sides. This will implies t cube plus 90 minus 2 square is equal to 27 1 plus t square, sorry, 1 plus t4 plus 2t square. So here you can use this identity to use a plus b plus c square is a square plus b square, or even without using that also you can say something. So this will give you a polynomial of degree. This will give a polynomial of degree 6, that is, because here you have no term of t raised to 6, and here you have one term of t raised to 6, so it will be a polynomial of degree 6, and that is satisfied by that is satisfied by 2 1 by 3 plus 3 1 by 2. Okay, so this also implies that degree of 2 1 by 3 plus 3 1 by 2 over q is less than equal to 6. Okay. Mm. So thus by the earlier part we get that degree of 2 1 by 3 plus 3 1 by 2 over q is equal to 6. Okay, so but we are using here So that completes the argument. If you're optional, or if the options are, you just have to check the options, then you can do that. But if it's a subjective question, still something more is needed to be done. So this is done after assuming q 2 1 by 3 plus 3 1 by 2. This field is same as, is isomorphic to the field q 1 by 3 3 1 by 2. So either you prove this or you use a trick. So this we have used here, right? To argue that it is divisible by 6. So the degree has to be greater than equal to 6, right? So uh, either we have to prove this, or if you want to bypass this proof, then you try to show that whatever polynomial you are getting, that polynomial is irreducible, or no polynomial of degree less than 6 satisfies this. So
Sir, last step,
yes,
that is less than is equal to 6, and then it is equal to 6.
so that is coming because using this we have already show we have already showed that 6 divides the degree. So if it is less than equal to 6 and 6 is dividing the degree, then what it can be the possibility, right? It has to be 6
Okay,
only.
okay.
So that's
Only one
why
possibility.
this is done once you assume this.
Sir, can we find here the basis of this element
The,
if
like
we want?
basis means like the
It is,
one we did in the class means
yeah.
so that on that I will come definitely. So before going there, it's clear that either we have to show this, or uh, if, so let me write more clearly. So either we should show this isomorphism, prove this isomorphism, or we can or so let me give this polynomial a name, a polynomial, say p raised to x px, okay, or uh, we should prove that the polynomial px is irreducible, or we can complete this argument by showing that there is no polynomial of degree less than 6 that is satisfied by 2 1 by 3 plus 3 1 by 2. So these three, at least one of these we have to do to ensure that the degree is 6. Okay. At present, we can only say that the degree is less than equal to 6. And that is even not enough to discard any single option, because all options are having degrees less than equal to 6 only. We use this thing to conclude that this is precisely 6. So either we prove this isomorphism, we are going to see this similar kind of question in I think third third question is similar to that, or yes, possibly the third one. Yes. So similar. So I will write similar uh, isomorphism. We will see in question 3. So let's try the second one if we can do that. Otherwise, we will move to the third one. First one is also true, but we will see that in the next one. So this one we are trying to see. Okay. So what is the polynomial? So this is t cube plus 90 minus 2 square. So we have to expand it. So t cube plus 90 minus 2 square, that is equal to 27 1 plus t4 plus 2t square. Okay. So yes. So expand it, you will get t raised to 6. Use this thing. Use a plus b plus c square is equal to a square plus b square plus c square plus 2ab plus 2bc plus 2ca. This is true if abc are in the commutative ring with unity, and here we are working with in q, so it will definitely hold. So this gives us t raised to 6 plus 81 t square plus 4, and then you have 2 times of this, that is 18 plus 18 t4. I will directly write minus 4 t cube minus 36t, and here you have 27 plus 20 plus 54 t square plus 27 t4. Okay, so after uh, solving it again more, we get t6 minus 90 square minus 90 square, sorry, 94 t6 minus 94 minus 4t cube plus 27t square, and minus 36t minus 23 is equal to 0. So to show that this polynomial is irreducible is not an easy job. So first thing you can see that we cannot use Isestian criteria here. So to show that this polynomial is reducible, is not easy. Okay. So now what with what option we are left with? We are left with showing that there is no polynomial of degree less than 6 that is satisfied by 2 1 by 3 plus 3 1 by 2. So now we will move to the basis argument that we uh, did in the class to actually conclude this. Okay. So I want to solve this also so that you realizes that why that argument was important, and sometimes we are not able to solve some questions without that argument, and that's why we should keep that always with us. So yeah, but that is also not an easy thing in that in here, because you can see 1 and then 2 1 by 3 root 3, and we will have the multiplication of them when we will be taking higher powers, so we have to include them as well. So this is root 3. Okay, first of all, its second power is also there, 2 by 3, and then the multiplication of root 3 with these two powers will also be there, root 3 2 2 by 3. They are linearly independent over Q. You can see that because you won't be able to write any one of them as a linear combination of other over Q. So let's start by looking at the basis, okay, using these elements. So first we have 1, that is of course 1 0 0 0. How many we have? 6 elements, right? Then t, which is 2 1 by 3 plus root 3. So that will be 0 1 1. That will correspond to, I should say, 0 1 1, and then 0 0 0. And then you have t square, that is 2 2 by 3 plus 3 plus 2 times root 3, 2 1 by 3. So that corresponds to what? 0, sorry, it should be 3 0 0 1, and then you have 2 and then 0. So this is, these two are linearly independent. This is also linearly independent. So till here we are getting linearly independent. Now, what if we get t cube? T cube is just take the cube of this. So uh,
Okay, I think fine, sir. We have to go now.
yes, we have to like do all these calculations to. So these are the three methods we generally use to say the degree. I will write quickly what is the final Q, and then we will move to the next question. So 3 2 2 by 3 root 3, and then 9 2 1 by 3. So this is 2 9 3 and 0 0 3. Again, you can see that this also still linearly independent. Okay, so still linearly
Yes, sir.
independent. Just two more I have to write, and then we will move. So T4 is uh, 2 4 by 3 plus 9 12. You might have got the solutions, but there all these details are missing. So, but one has to check all these details to ensure that the degree is exactly 6. If it comes as a optional question, then it's fine. Otherwise, you have to do all these things. So this will corresponds to 9 2 8 18 12 and 0. So it has again 0 at the different places. So this still remains linearly independent. And if you look at T5, then it will be 60 plus, so I will just write whatever the basis form is: 60, 45, 9, 2, 10, and 30. So it has all non-zero parts here, and every other at every other place you have zeros. So this still remains linearly independent. And then after T6, so this from here only you will get that.
6, 1, 2, 3, 4, 5,
Okay, so till degree 5 you are not getting anything. Okay, so this implies that uh,
6.
no, it doesn't imply 6. It implies it has to be greater than equal to 6. This implies that this does not satisfy a polynomial in Q, sorry, a polynomial of degree less than equal to 5 over Q. At 6, it may or may not satisfy. We haven't checked that. We haven't find the polynomial precisely. We have just seen that till T5, it won't satisfy. This will implies that Q 2 1 by 3 plus 3 1 by 2 over Q has to be greater than equal to 6. Now, if we make use of the earlier argument, that this argument, where this argument that it is satisfied by a polynomial of degree 6, we are done, right? So, and we have already seen that 2 1 by 3 plus 3 1 by 2 satisfies a polynomial of degree 6 over Q. So this implies we have the equality. So now there is no gap, and this completes the solution. We can also do it by two other ways, but this one we will see in the next question. Similar argument will be there, and this one is not easy to do. But if you just want to like tick an option, you can go with that. Okay, I hope this is fine. So I gave a lot of time over it because I thought that that will be beneficial for other solutions also, because it somehow relates all other questions also. Okay, so now we can move to the next question. Let me just copy paste it. Yeah. So it says, what is the degree of Q root 2 root 3 over Q root 2 plus root 3? Okay. So that we have to see. Solution. So one thing is clear, that since
So
Q,
both are identical.
yes, but we have to say why. Okay. So
Okay.
Q root 2 and root 3, they are inside Q root 2 root 3. Therefore, you have Q and root 2 plus root 3 inside Q root 2 root 3. And Q root 2 plus root 3 is the smallest field containing q and root 2 plus root 3. So this implies that q root 2 plus root 3 is inside, is a subfield of q root 2 root 3. Okay, so one way implication is easy. Other way we have to do. So also you have root 2 plus root 3 inside this is one equation, you can say root 2 plus root 3, and since this is a field, we have the inverse of it, that is uh, that just rationalize it, it will become root 2 plus root 3, that will become root 2 minus root 3, a plus b, a minus
minus
b. It should be
in
minus.
the denominator. Yeah.
Yeah. So it will give you 2 minus 3, that is minus 1. So that is same as root 3 minus root 2, right? This is also inside uh, q root 2 plus root 3, right? Because it's a field, so its inverse, if something is inside it, so its inverse will also be inside this. Now what? Root 3 plus root 2 plus root 3 is there, root 3 minus root 2 is there. This implies uh, root 3, that is root 2 plus root 3 plus root 3 minus root 2 and divided by 2, right? This is also inside q root 2 plus root 3 and root 2, which is root 2 plus root 3 minus root 3 minus root 2 by 2. This is also inside root 2 plus root 3, and that implies that this field q root 2 root 3 is also inside is also inside q root 2 plus. Okay. Yeah, I hope that is okay. Hmm. And uh, from first and second, this implies that they are same as a field, and thus the degree of q root 2 root 3 over q root 2 plus root 3 is equal to, okay. So this is again an easy question, I guess. So let's see the next one. If there is any doubt, then you can ask.
No, sir.
Otherwise,
Clear.
okay. So next question first defines the Isestian criteria, and then because it's an assignment one, and in week one we didn't see the Isestian criteria, so it first defines it and then ask us to find the roots of a polynomial. So it says, so Isestian criteria, let's revise it. So it says that it states that a polynomial p equal to a naught plus a1x plus a2x so on with integer coefficients is irreducible if there exists a prime p such that p divides a naught, p divides, yes, a naught a1 so on to an minus 1, p does not divides an, and p square does not divides a naught. So we have to use this criteria to see how many roots are there of the polynomial x cube minus 2 in the field q. Okay, so this we have already seen in the question number 2 itself. But let's again see this. So we have here px to be x cube minus 2. So we can take uh, prime p is equal to 2. So there is a very bad notation thing here. So uh, instead of p, it should be px. We are overusing the notation, denoting the polynomial with p and also the prime with p. So uh, you can correct here that it's px. So take prime p equal to 2, then of course p divides a naught, that is minus 2, and a1 to an minus 1. Oh, sorry. Here an minus 1 is nothing but a2. So a2, that is also 0. P square, that is 4, does not divides a naught, and p does not divides an, which is nothing but a3. So this implies x cube minus 2 is irreducible over uh, q. So it has no roots in q. So the answer is 0. So it has 0 roots in q. Okay. Okay. So now we can move to the next question. Is it fine till now?
Yes, sir.
Okay. So let's uh, move to the next. So it says the same polynomial, but the field is now changed to qi. So what's your guess? It should be true or false?
I think it is false, sir.
This is reducible.
Yeah.
And what are the factors then?
I think the second factor.
Second factor means,
So simply I mean to factorize as a linear factor.
so all three will be linear factors.
No, first is x minus cube root of 2, first factor.
Okay.
And, and the remaining two factor will go in, I think, complex number.
So 2 1 by 3 is inside uh, qi.
Q. No, sir.
Then how you can write it as a linear factor?
Means we can factorize as a linear factor, but in different field.
So,
We
but
can say it is uh,
and
cube root
how?
of 2 belongs to real number. We can say.
Yes, but we are supposed to write polynomials in qi. X minus this polynomial x minus 2 1 by 3. This is not inside the polynomial ring of qi. So we cannot
Okay,
write
means the first,
this factor.
yeah, first factor is qi. Yeah, that's fine, sir.
So you cannot write uh, x cube minus 2 as x minus 2 1 by 3 some 2-degree polynomial in
Yeah.
qix, because this polynomial is not there inside qix. You have to
Yes, sir.
factorize inside the field. Na? What it?
Yes, yes, yes.
Uh, then what to do? So assume that x cube minus 2 is reducible over qi. If it is reducible, uh, then there exists fx and gx in qix such that x cube minus 2 is fx dot gx, and also the degree of fx is 1 and degree of gx is 2, because the sum of degrees should be equal to 3. So and it has to be a non-unit, so the degree has to be greater than equal to 1. The only possibility is one polynomial is of degree 1 and the other polynomial is of degree 2. Now gx may be reducible or irreducible, so it may again factorize linearly in two factors or not. That's a different thing. But if it is reducible, that x cube minus 2 is reducible, then it should be written in this way only. That there is just a polynomial of degree 1 and there is just a polynomial of degree 2, such that their product is equal to x cube minus 2. Clear?
Yes, sir.
That's what reducibility says, right? You can write it as a product of two non-units. So non-unit means the degree has to be greater than equal to 1, and the sum of degrees should be equal to 3. So the only possibility is 1 plus 2. Okay. And then again, as I said, that gx may be a product of two linear factors or an irreducible polynomial of degree 2 that we don't care about, but it's a polynomial of the degree 2. Okay.
That means, that, sir, if any factor is
Mhm.
irreducible in that field, that means the complete polynomial is irreducible, na?
No. So
If
reducible,
any one factor.
no.
Here
Reducible,
is fx is already irreducible,
yes.
and if gx will be reducible,
Then we won't
then
say that x cube minus 2 is reducible. Irreducible means you cannot write it as a product of two non-units. If you are, even if you can write it as a product of two irreducibles, fine.
okay,
You have reduced that polynomial in smaller polynomials.
okay, done, sir.
Okay, so means if you say fx is a polynomial and you can write it as gx dot hx, where gx and hx are both irreducible polynomials, then we will say that, still say that fx is reducible, because we have reduced it as two product of two polynomials which are non-units, right? So components may be reducible or reducible, doesn't matter. Only thing is whether we can write it as a product of two non-units or not. So if it is reducible, then we should be able to write this like that, and such that the degree of first polynomial is 1 and the second is 2, or vice versa. Maybe you can write the degree here is 2 and here is 1. That won't matter. We are in commutative ring. Okay. So this is the case. So this implies, if that is so this is a linear factor, right? It's a uh, 1 degree factor, and thus this implies that there exists some alpha belongs to qi. All these things we are doing in qi, right? In qi, such that fx is nothing but x minus alpha, some linear factor. Okay, so this implies x cube minus 2 is x minus alpha dot gx, and which implies alpha is a root of x cube minus 2. ठीक है? And alpha is also lying inside q of I. Now consider the tower of fields. So the following actually, consider the following tower of fields. So one more thing to notice is alpha cannot belongs to Q from question number 4. We have already seen that uh, this polynomial is irreducible over Q. So if alpha belongs is a root in Q, then we can write x minus x cube minus 2 as x minus alpha times something, and that makes this polynomial reducible. So since this is irreducible, it won't have a root in Q, right? Keep this thing in mind that the converse may not be true, that a polynomial may not have a root in the field. Still, it might be reducible because you can write it as a product of two irreducible factors. But if it has a root, then it is definitely reducible because it has a divisor of the form x minus alpha, where alpha is a root. Okay. So since it is irreducible, it cannot have a factor of the form x minus alpha. Thus, thus alpha is not a root in Q. So it's a root in Qi, but alpha won't belongs to Q. Okay. Now consider the tower of fields. So um, Q is there, and then you have Q of alpha is there, and then you have Q of I is there, right? So what is the degree of Q of I over Q?
2.
Okay. So very bad drawing. So this has degree 2 since I is not inside Q and I satisfies uh, I satisfies x square plus 1 over Q. So it has degree 2. And what is the degree of this? So alpha satisfies
Degree
x,
3.
yes, x cube minus 2 over Q. So alpha is not inside Q, right? Alpha, this has degree 3 since alpha is not inside Q, right? So definitely the linear factor is not possible, and alpha satisfies x cube minus 2 over Q. And also this polynomial is, we have already seen, irreducible over Q. So the degree cannot be less than 3. Okay. So it has degree 3, and so here you have 3 and here you have 2. Can it be possible? This is a contradiction to Q I over Q is equal to Qi uh, Q alpha and Q alpha Q. This is a contradiction to that because this is 2 and here you have
3.
3. So 3 won't divide 2. So this is a contradiction, right? So why this contradiction? This is a contradiction, hence x cube minus 2 is irreducible over qi as well. Okay, so yes, clear. Okay, so let's move to the
Yes.
next. Okay, so let's move to the next question. It says which of the following are isomorphic to qt t square by 3. Okay, so it is isomorphic to the first one. Why? Since this field is what? So I should not say field now, because so this is modulo the ideal generated by t square minus 3. So you can use the Euclid division algorithm. So if you have a polynomial of degree uh, more than 3, sorry, more than 2, then you can divide by t square minus 3. And uh, so what I mean to say that if pt belongs to qt has degree greater than equal to 2, then what you can do, then you can you can write this as, then pt is equal to some qt times t square minus 3 plus rt, where degree of rt is equal to 0 or 1, right? You just use the Euclidean division algorithm over this ring. And so if you do the modulo thing, then this part is 0 and you are just left with rt. So this polynomial, this ring has uh, classes of the polynomials with 0 degree or 1 degree only, right? And so this is equal to same as saying that these are the polynomial of the form a plus b root 3 such that ab belongs to q. Okay, and that is same as the polynomial. So one evaluation map we have seen, right? The saying pt to p of alpha. So that is what this is. So you are sending this rt to r of root 3, which is the root of t square minus 3. So this will be mapped to this. So rt is of the form a plus b t, right? It's a linear polynomial. So that's how the image of all these polynomials under this isomorphism will look. And it's an isomorphism. And this is same as q root 3. Okay. So that's also we have seen. So the first ring, so the first is isomorphic. So first is a correct option. There's an isomorphism, I should write it. Okay. What about the second? The second one is t square minus 4t plus 1. So if it is isomorphic, then we must have the same root. So t square minus 4t plus 1 also should have the same root. So qt minus you have t square minus 4t plus 1, this polynomial, this ring. So what are the roots of this polynomial? So
Or 2 plus minus
yes, it has roots.
root 3, I think.
So just we do this thing, minus b plus minus root of b square, that is 16 minus 4 upon 2. That will be 2 plus minus root of 3, right? So uh, this implies that q t modulo t square minus 4t plus 1 is isomorphic to the field q. This is a irreducible polynomial. First of all, this is irreducible in q. That's
Minus
why it's a field.
root 3. 2 plus
So 2 plus minus root 3 adjoint 2 plus root 3 and 2 minus root 3, and 2 is already there. So this will be same as q root 3. Okay. So the first two are correct. What about the third one? Let me go back. So it says t square minus 2t minus 5. Oh, I am not using correct color. Just a second. So third one is q qt modulo t square minus 2t minus 5.
sir, 1 plus minus root 6.
1 plus
Roots.
minus root 6. Yes. Okay. So good. It has roots t equal to 1 plus minus root 6. And this implies that this field qt modulo t square minus 2t minus 5 is isomorphic to q root 6, right? But
Yes, sir.
that is not same as
Belongs to q root 3.
q root 3. Got, because root 3 and root 2 root 3 they are linearly independent over q. So this will be the case.
And
Now
the
the,
last one is also, sir.
yeah, last one is also not there. So it
1
says,
plus minus root 3. It's root.
just a second, qt modulo t square minus 2t minus 2. This gives you, it has roots t is equal to 1 plus minus root
3.
3. So this is okay, right?
Yeah.
So this implies q e t square minus 2t minus 2 is isomorphic to q root 3. Okay. So yes, now that is fine. So let's move to the next question. It says which of the following are quadratic extensions. First one, what you want to say? So clearly, this is isomorphic to q root 2, right? And should not use square brackets. So this is isomorphic to q root 2, right? And that the degree of q root 2 over q is 2, because the given polynomial is irreducible over 2. You can just use the Eisenstein criteria and that's it. Other way to see is root 2 is not inside q and it satisfies the polynomial of degree 2. So it has to be, the degree has to be 2. Yes. The second one uh, is okay. B1, uh, similar to, we have already seen such a situation earlier, similar to question number 3. uh, we can show that q root 2 plus root 5. There we have root 2 plus root 3. Here we have root 2 plus root 5. And that is isomorphic to q root 2 root 5. And then it's a extension of q root 2. And that's an extension of 2q. So it has degree 2. And that also has degree 2, right? Because root 5 satisfies x square minus 5 here, and that is irreducible not only on q but also in q root 2, that you can check. um, One thing to see that is clearly root 5 is not inside q root 2, because you cannot write it as a plus b root 2, and root 5 satisfies x square minus 5.
Q root
No,
5.
no, x square, if you take it will be 5 na, x square minus 5 over q root 2. Anyway, root 5 is not inside q root 2, so you cannot write it like that. Okay, so this is not inside q root 2, so the degree must be greater than equal to 2, and it satisfies the polynomial of degree 2, so the degree is precisely 2. And also the degree is 2. So mm, this way we get that the degree of root 2 plus root 5 over q is 4. Okay, so this is not a quadratic extension. This is not a quadratic extension. What about the third one? So it's the root of the polynomial
I think its roots are 3 and 2 only.
yes. So this is nothing but t minus 2,
T minus
t
3.
minus 3, right? So uh, in C part, what we have, t square minus 5t plus 6 is equal to t minus 2, t minus 3. This implies alpha is equal to 2 or 3, and which implies q of alpha is nothing but q. So again, it's not a quadratic extension, it's just q. So the degree is 1. Okay. So here also we get q alpha over Q is not a quadratic extension. In fact, it's just the same. What about the last one? It is QC4. C4 is E 2 pi eta by 4. Q, fourth root of unity. QC4. Fourth root of unity is nothing but iota, na? So C4 satisfies x4 minus 1 over q, because that's how the C4 is there, and it generates all other roots of x4 minus 1. That is what the definition of primitive root is, right? And Cn means the primitive root of xn minus 1. So also x4 minus 1 is what? This is x minus 1, x plus 1, and x square plus 1. So
These are linear.
yes, these are
And
linear,
Q.
and C4 is not equal to 1 or minus 1. So it won't satisfy this point in this part, and it satisfies this. That means this implies C4 satisfies x square plus 1, right? And
Plus minus I here.
plus minus I, you can say, and without even going into that complex theory, also you can say this satisfies this, and C4 is not inside Q, right? Because it's a
Yes, sir, definitely.
okay. This implies uh, the degree of Q C4 over Q is 2. Right? Satisfied 2-degree polynomial and not equal and not inside the field. So this is a quadratic extension.
Right, sir.
Okay. So let's move to the next question. It says, so discriminate let D be defined so that Qt modulo T square minus 2T minus 4 is Q root of T. What is the value of T? So that D was the discriminant. So solution for any polynomial 2-degree polynomial 2-degree monic polynomial, let's say x square plus ax plus b. D is nothing but root of t, any alpha times a square minus b, a square minus 4b. Okay, so this is the discriminant, means as we used to write for ax square plus bx plus c, it is b square minus 4ac, right? So similarly for this polynomial, this is a square minus 4b, and any uh, uh, alpha belongs to q. Any multiple of it will also work, because this won't create a problem in the field extension. Q of root of 2 is same as Q of 2 root 2, right? So that multiplication by the field element is not won't create a problem. So up to that you can vary. So here uh, D is a square, that is minus 2 square minus minus of 4. So that is 4 minus 4 plus 4 minus 4 times 4 also there. So here a is equal to minus 2 and b is equal to minus 4. So a square minus 4 times 4, that is 4 minus 16
20.
of 4 plus 16, that is 20, right? There is some typo in the solution or what? Yes, yes, there is a typo there. So what typo is there? So instead of d, either one should write root d or d. Either write root d here or
Root D.
root d here. So that's a problem. So this is root d I am doing here. Okay. So then this alpha thing vanishes, and we will do adjust this alpha in the final argument. So root d is root of 20, which is 4, uh, sorry, 2 root of 5. So this implies qt is qt modulo t square minus 2t minus 4 is q 2 root 5, and that is same as q root 5. So we can take d to be any alpha times root 5 such that alpha belongs to q. Okay. Okay. So yeah, let's move to the next one.
Sir,
Yes.
their value will be root only 5 na, or 2 root 5?
Where?
In the previous question,
Here you are saying?
D is 20. So root D is, that is 2 root 5 na?
Yes.
The value of root D, that is the question, or only value of D only?
Value, that's what I said. Nah, there is a typo. Here it should be root d. What is the value of root d?
Okay, okay, only root D, that is 2 root 5 na?
Uh,
Okay, sir.
That is 2 root 5, but you can like, so that you can take any multiple of root 5 because 2 is already there inside q. So that is same as saying the question says let d be defined so that qt modulo this is q root d. Okay. So then what is the value of root d? So you can take root d to be root 5 or any q times root 5. The field will be the same. Okay.
Okay.
Clear? So
Yes,
here
sir.
there was a typo. It should be root d instead of d. Okay. Okay. So yes. Now it says what is the value of qc8 over q? So we will go by the definition, and So C8 satisfies,
It's x8 minus 1.
yes, so it satisfies x8 minus 1 and it
x4
generates,
minus 4.
yes, it generates all other roots of x8 minus 1. So now x8 minus 1 is same is x4 minus 1 and x4 plus 1, right? So you can expand this and then check that C8 is not a solution of this x4 minus 1, or one way, other ways to see is, so if C8 satisfies uh, x4 minus 1, then uh, C8, uh, so this means that C8 is a root of, is the fourth root of unity, is a fourth
Yes,
root
sir.
of unity, right? So it cannot generate the other roots, other eight roots of unity. This means this will imply C8 cannot generate the other eighth root of unity, because it can only generate the fourth root of unity, and uh, that they are four in number, but x8 minus 1 has eight roots, so it won't generate the all of them, right? It can generate at most four. This is a contradiction. So this implies x4 C8 satisfies x4 plus 1 over q. But the question is not yet complete, because we also have to show that x4 plus 1 is irreducible. And how to do that? Any idea? So of course the isosterian criteria won't work.
It's 4 plus 1.
So we will use this lemma. Let fx belongs to f of x, then fx is uh, irreducible over fx if and only if f of x plus a is irreducible for every a belongs to f. Okay, and what is the proof of it? A very simple proof. So let fx be reducible, then fx is equal to some gx dot hx, right? And that will implies that fx plus a is what? G of x plus a dot hx plus a, and which implies that f of x plus a is also reducible for all a belongs to q, right? Parallelly, if fx plays reducible, for some mm, for some a, this will implies that fx plus a is gx plus a hx plus a, and you can just replace x by x minus a, and this will implies that fx equal to gx dot hx, and thus fx is reducible. So we have proved the contrapositive statements, that if fx plus a is not reducible, it's not irreducible, then fx is not irreducible, and if fx is not irreducible, then fx plus a is not irreducible. Okay, so yeah, so that completes the proof of this one lemma. So instead of showing x4 plus 1 is reducible, we will show that x4 uh, plus, so let's say this polynomial I am naming as p of x. Okay, then we will show that f sorry,
Sir, here value of A will be 1 only.
yes, yes, 1, yes.
Okay.
So p of x plus 1 is irreducible. We can take any one for which we can show. If we can show for any a, then it means that we are done. Okay, so that's a thing. A is of our choice.
Okay. Any arbitrary, that is.
Any arbitrary you can take. If it is satisfies for one a, then it will satisfy for all a's, because you can do the translation. Okay,
Okay.
say if you do it for x plus a, and if you want to see for x plus b, then the above lemma says that you can replace x by any x plus alpha. Alpha belongs to the field, so you can just write here x b minus a, and you have a, so that is x plus b. Okay, so if it works for one a, then it will work for all b. Similarly, if it fails for one b, it will fail for all a. Okay, that's why the choice of a is in your hand. You just need to check for one a, the reducibility or irreducibility, and then it will work for everything. We will show that that p x plus 1 is irreducible. So p of x plus 1 is what? This is x plus 1 raised to 4 plus 1. So use binomial expansion. So that is x plus x4 plus 4 uh,
X4 plus 4x cube plus 10x
yeah.
square, I think. Plus 4x plus 2.
So this is 4x cube plus 6x square plus 4x
Plus
plus
2.
1, and so that's what the binomial theorem says now. Xn plus nc1, xn
And
minus 1,
C2.
and nc2. So
Yes, sir.
this is 4c2, which is 4 factorial divided by 2 factorial and 2 factorial. So you will get 3 into 2, that is 6. Okay. So
Yeah,
this
done.
x4 plus 4x cube plus 6x square plus 4x plus 2.
Plus
Now you
2.
can apply
Einstein criteria.
Einstein criteria. For p equal to 2, p divides 2, 4, 6, and 4,
Does
and
not divide 1.
p does not divide 1, and p
P
square
square also
does
does
not
not
divide
divide 2.
2. So this implies px plus 1 is
Irreducible.
irreducible over q by Einstein criteria. And thus px is irreducible over Q, and which implies uh, x4 plus 1 is a irreducible is an is an irreducible polynomial over Q that is satisfied by C of 8. Okay, and thus Q C8 over Q has degree
4.
of 4. Thanks. Okay, okay. So if that is fine, we will move to the next question. So again, the true false question, it says that a square with the same area as an equilateral triangle of side 1 is constructible or not. So we have to first see what is the area of an equilateral triangle, and then using that formula we will be solving this. So area of an equilateral triangle of side say L is root 3 by 4 L square. So this is easy to prove, and I'm not proving it. So here what we have, here we are given that L equal to 1, side length 1. Okay, so this means we want to construct a square of side S of side S such that the area of the square, that is S square, is equal to root 3 by 4, right? This is area
Yes,
of the
sir.
area of the square, and this is area of the equilateral triangle. Equilateral triangle of side length 1. So we can construct this if and only if we can construct this number as this implies this square is constructible. This square is constructible if and only if S is equal to the, root 3 upon 4 is an constructible number. Now what? Now we will be using a theorem that we have already seen in the class, which says any real number R is constructible if and only if there exists a tower fn fn minus 1 fn minus 2 and so on to f2 f1 and then say tower with end at q such that the degree of fn over fn minus 1 is, sorry, I, let me write I, so degree of fi over fi minus 1 is 2 for all, uh, this is 2 for all I inside 2 3 n so on to n, and degree of f1 over q is also 2, this is comma, and your a belongs to f. Okay, so if you have such a tower of fields, then only so it's an if and only statement that then only this a is constructible or not. Okay, and as a corollary of this we get that if a belongs to r is constructible, so if a belongs to r is constructible, then from the above theorem we will get this tower, and then uh, we will get that this extension q of a over q is equal to 2 raised to n for some n belongs to this capital N. Okay, may not be the same n, I think it will be n plus 1 or something, but uh, uh, let me write m only just to avoid the notation confusion, because n I am also using in the theorem. 2 raised to m for some m belongs to n. The converse of this corollary may not hold, that if it is of the form 2 raised to m, then it's not necessary that this is constructible, because this tower may or may not exist. Okay, but one side corollary is true, the theorem is true both side, that if there is a tower of such a tower, then it is constructible, uh, and otherwise not. Or the corollary says that if it is constructible, then the degree must be of the form 2 raised to n. Okay, but keep this thing in mind that the corollary is not two ways. It doesn't mean that if the degree is 2 raised to m, then the number is always constructible. Okay, for example, if you take so this is for r, otherwise I would have said 8, you can take a to be iota, but there can be degree 2m extensions for which a is not constructible. You have to find the tower in that case. Okay, okay, so we have to see that this is constructible or not, and for that uh, how to mm, proceed, we have to find a tower, right? So see, since, so this is let me just put it in brackets, this is the revision part. Okay, let's get back to the question again. So the degree of q root of 3 by 4 over, oh, oh, an error I have done. So this is what, uh, this is nothing but uh, root of 3 by 2, right? And this 2 is already inside q, so we can remove that. So this is a constructible number if and only if 3 1 by 4, that is root of 3 is constructible, is constructible. Okay, so you can check that the degree of 3 1 by 4 over uh, q 1 by 2 is 2, because uh, 3 1 by 4 satisfies this twice x square minus 3 1 by 2 over q 3 by 2, and 3 1 by 4 is not inside q 3 1 by 2, and also q 3 1 by 2, it has degree 2 over 2, over q it has degree 2. So yes, so we have got a tower of fields, each of degree 2. This is q, you have q 3 1 by 2, and then you have q 3 1 by 4. From here to here you have degree equal to 2, and from here to here also you have degree equal to 2. Okay, okay, so this implies 3 1 by 4 is constructible, and that implies the square with area uh, root 3 by 4 is constructible. Okay, uh, mm, so here I have an only the statement. Yes, okay, so if that is fine, we can move to the next question. Okay, so I hope this is fine. So let me write question number 11. So it says, which of the following are not constructible numbers? So C4 we have already seen. So C4 is a imaginary number. So yes, but you can consider that number as what to say. Mm, yes, so as a length of uh, the triangle with sides 1 and 1, not that precisely. So uh, what I mean to say is, although C4 is not a real number, but you can still say that it's constructible because it has extension field of extension 2. So you will get a tower, and thus uh, it is constructible. So although that statement is for real numbers, but that just mean that you are in a different axis. If you have a plane with x and y axis, so imaginary number means you are at a different axis, and on that axis you can construct that I. So that's why we say that it is constructible if it is containing a uh, tower of extensions of degree, each of degree with each degree of with the degree of each extension to be 2. So still, even if it is imaginary, we will say that it is constructible because it's just a shifting of the axis from x to y, so it won't matter as such. So the a part is true because you have q of c4 over q to be 2. So, and you have this extension of degree 2 extension. So despite the fact that this number is imaginary, we can say that it is constructible because it's just a shifting of the axis from x to y. If you are in xy plane, y represents the imaginary part and x represents the real part, then it's just drawing it on the other axis. So it's if it is having a degree 2 extension, we will say that it is constructible. So this is okay. The b1 b part we have already seen root 2. Since q root 2 has degree 2, so this is also fine, degree 2 extension. This is also done. Now 2 root, so c1 is 2 1 by 2 plus 3 1 by 3, and similar to question number 2, similar to question 2, one can see that degree of q 2 1 2 plus 3 1 3 over q is 6, which is not of the form 2m. So this option is not correct. This is not constructible. So this implies 2 1 by 2 plus 3 1 by 3 is not constructible. And D part, which says that 2 root 2 plus 3, so 2 1 by 2 plus 3 1 by 2, this is constructible because you can get a, so we have already seen that 2 1 by 2 plus 3 1 by 2 as a field, they are same, it is same as uh, q root 2 root 3, and which is a degree 2 extension of root 2 q root 2, and which is a degree 2 extension of q root q. So it has degree 2, and this also has degree 2. So this implies this number is a constructible number. Okay, so this is question number 11. Now let's move to the question number 12. We will discuss one or two more, and then uh, if time gets over, then we will continue in the next lecture. So this question is easy once you understand the Gauss theorem. So Gauss theorem says that a regular n-gon is constructible if and only if uh, uh, n equal to 2 some power of 2 times some distinct powers, distinct Fermat primes. What Fermat primes are? They are primes of the form 2 raised to 2k plus 1. So if n is of this particular kind, that it is some power of 2 times some distinct primes, and each of them is a Fermat prime. So Fermat prime is just 2 raised to 2k plus 1. Then if the n has this particular form, then only we can say that regular n-gon is constructible. So it's an if and only if condition. So yeah, so using that, let's see which of the following numbers are forward values of n are the following n-gons constructible. So a is 5, which is 2 square.
2
So
square plus 1.
2 square plus 1. So here, of course, this part is not there, but we are not worried about it. It should be of this form. A can also be 0, because here a is some non-negative integer. So positive or 0 is allowed. So this is 2 square plus 1. So this is a Fermat prime.
Constructible.
Fermat prime. So this implies that a regular 5-gon is constructible.
17
B is 17, which is 2 raised to 4
2
plus 1.
plus 1. Again
Again, it's
comes
a Fermat prime. So this also implies that regular 17 gon is constructible.
33 also.
33 is,
So we can write 3 into 11.
we cannot write 33 as 32 plus 1, because it's not a prime. Okay.
So 3 into 11, and then 3 can be
Yes. So first of all, this is not allowed. Let me clarify that. That's why this 33 number is being put, because people can try to write 25 plus 1. This is not allowed, since 33 is not a prime. It's not a prime. We have to write it as in the prime factorization form, but 33 is 3.11. This is 2 plus 1 Fermat prime, but this is uh, 2 cube plus 3, not a Fermat prime, right? Thus
2 cube
33
plus 3.
regular 33 gon is not constructible.
Sir, but 11 is prime number, na?
But it's not a Fermat prime, na? We need Fermat primes.
Okay, means all the numbers should be in Fermat prime.
Yes. And we need distinct Fermat primes, that is of the primes of the form 2,
Okay,
2 raised to
okay,
k
sir.
plus
Okay,
1.
right.
So 11 is not of this form.
Yeah.
Regular 33 gon is not constructible. So it's a very important theorem, because it gives a if and only statement. A complete characterization is there. Okay. D is another interesting case. 409, sorry, 1028 is 1028. So first of all, divided by 2, that is 514. Again divided by 2, that will be
2 raised to, I think, 10.
257. So this is 2 square times 257. Now what? 257 is a prime or not? One has to check. So mm, this is
0.7.
prime since it is not divisible by 2, it is not divisible by 3 also. Some of the digit is 14, right? It is not divisible by 7 also. You can see if you divide by 7, the remainder is 2. 337, yeah, remainder is 2. Then the other, next prime is 11. For 11 we have the division.
15,
Yes, 11 will also
15,
13. If you divide 13, then it will be 12 and 12, 127, right? You will get remainder 10.
no, sir.
And what about 17?
No, it's
17 will give you 887. No, right? 2 is the remainder.
19, 6,
19,
no,
667. No.
21, 4, no, 23, 2, no, 29,
Whether we need to go
20,
that much behind, that much. See, what is the square of 17?
289, I think.
289. And it is already greater than 257, right? So we need not to check this much, because
Okay, okay. Yes.
if a bigger number divides it, then it should be some bigger number times a smaller number, right? But we have already seen the smaller numbers are not dividing. So we need not to check for other primes, right?
Okay, sir.
Just check for till a prime whose square is less than 289, 257. Okay. So this is a prime, and also 257 is of the form 256 plus 1, and 256 is 2 raised to 8 plus 1. So this is a ferment prime, and which implies regular 250, this 1028 gone is constructible.
Constructive.
Over, already gone past the time, but let's quickly see the one or two more questions. I think uh, the next two we can see, and then we can stop, because they are directly an application of this uh, this Gauss theorem. So we should see this. Otherwise, we have to revise the Gauss theorem again in the next class. And then the last one and assignment 2 we will see in the next lecture. Okay, so this is true or false. Cos 2 pi by 3 is constructible or not. Okay, so solution is cos 2 pi by 33 is constructible if and only if the angle 2 pi by 3 is constructible, 2 pi by 33 is constructible, and that is if and only if a regular 33 gone is constructible. And this holds by the last questions, 12C, right? So by 12C, uh, cos 2 pi by 33 is constructible, because we can consider construct a 33 gone, we have seen. Or sorry, not constructible, nah? It's not constructible, because 33
Is
is,
not constructible,
yeah, 3 into 11, and 11 is not a Fermat prime.
not in the Fermat prime.
Yeah. Okay, then the last question for today's discussion is again for constructible number. It says which of the following are constructible numbers. Cos pi by 5, root 5, 2 1 by 3, and all these things. So first one, this is okay since 5 is equal to 2 square plus 1, right? Fermat prime.
Yes, sir. Constructible.
So this is Fermat prime. This is also okay because the degree of the field extension
2.
containing root 5 is 2, right? So it has a
Yes, sir.
tower of extension 2. This is not
2 cube root
constructible
is not.
because
Degree 3.
degree 3. So this is a one-side statement. Okay, always keep this thing in mind. If it is uh, some 2 raised to something, then we cannot assure by just this.
Yes.
Okay, we have to find a tower.
Okay.
But here it is just 2, so it's definitely Q is a subfield of this, so we have a tower. So by the corollary, this is not the case. And similarly, this is not, because this 2 1 by 3 is not constructible. So how will you construct this number? Okay. So this is by C. So this is not constructible. Thus, this number times something is also not constructible. Okay. That's
Okay,
it.
sir.
So we will see the
Let's see.
15th question and assignment number 2 in the next lecture. Okay. Any doubt?
So 10th number question I have missed, I think because of poor connection.
Okay. So let me go back again to take question number 10. It says a square with the same area as an equilateral triangle of side length is constructible. This one,
Sir, next slide.
your voice is breaking. This one,
Sir, down please. Hold down.
you want me to scroll down?
Down. Okay.
Uh, 10th,
Constructible. 3, 4.
yeah,
Number 10th. Number 11. I think 11.
11 number you want me to repeat?
11.
I think this.
Sir, in the 10th question, the last I have written satisfaction x square minus root 3 is over q.
Okay. So this part you want me to explain?
Yes.
So, so let me just start from the beginning. It won't take much time. So it says whether a square of the area same as an equilateral triangle of side 1 is constructible or not. So area of an equilateral triangle is root 3 by 4 L square. Length is 1. So it will be root 3 by 4. So we can construct a square if its side, that is S, has square to be root 3 by 4. So this square is constructible if and only if the side of length root 3 by 4 under root is that is constructible. So that is root 3 again under root by 2. 2 is a rational number, so you can ignore it, and then it is just 3 1 by 4. Okay, so the square is
Okay.
constructible if and only if this 3 1 by 4 is a constructible number. And we saw in the lecture that A belongs to R is constructible if and only if there exists a tower of fields such
Yes,
that
yes. Is it
each one
right? Yes, sir.
each one has degree 2 and A belongs to this Fn. Now A belongs to corollaries. If A belongs to R is constructible, then the degree of QA over Q is 2 raised to m for some m. So but here we need to show, we want to show that this is constructible, so we can't use this corollary because this is for something that we want to show not constructible. If that is power is not 2m, then we can use that it is not constructible. But for the other side, we have to use this above theorem, right? So we are trying to construct a tower. The tower is like this: Q, then Q root 3, that has degree 2, and then Q 3 1 by 4. That has degree 2 over Q root 3. Why? Because Q 3 raised to 154 is not inside Q root 3, right? Q root 3 will contain elements of the form A plus B root 3. It won't contain 3 1 by 4, right? That is root 3 again root 3. Root 3, then again its root. So its degree has to be greater than or equal to 2, but it also satisfies the equation x square minus root 3 over q root 3. So it is root 3 is inside q root 3, so this polynomial is inside q root 3. So this satisfies this polynomial, because if you take the square of this will be 3 root 2, and then 3 root 2 minus 3 root 2 is 0. So it satisfies the degree 2 polynomial, and it is not inside q root 3. That's why the degree is 2. So that's how this tower is constructed, and thus 3 1 by 4 is constructible. So the square with area root 3 by 4 is constructible. Okay.
Yes, sir. Now fine.
Okay. Anything
Okay,
else?
sir. Thank you. No, sir. Nothing else.
Okay. So we will have the next session on Tuesday from 6 to 8 at our usual time. Okay. And then there we will first solve the last question for assignment 1, and then we will solve the assignment 2 also.
Okay, sir.
Okay.
Thank you.
Bye.